Hello everyone. Let's start tutorial session. The first talk given by Professor Santa Saka. Just a moment. Professor Santa Saka received a PhD degree in the mathematics from Indian Statistical Institute, Kolkata, India in 2011. He is currently professor with IIT Madras. He was guest researcher with NIST USA. His main research interest include cryptography and number theory. Okay, today talk is please start. Santa. Okay. Thanks.
Okay, thank you, Jaganari, for nice introduction. And today I will discuss about lattice attacks on RSA. So this is my plan. I will first start with RSA. I know that you know RSA system very well, but I again will recap that famous algorithm, this famous algorithm. Next, I will discuss lattice. And lattice is not new subject. Mathematicians are using lattice from Gauss time and perhaps earlier than Gauss. And we'll use lattice to construct new crypto system. But today we'll use lattice to break RSA. So not to analyze RSA instead of talking about break. And finally, we'll show that how we can use this lattice idea to analyze RSA.
না সাপোর্ট করছে না ফাইল এটা কি ফুল স্ক্রিন করে দিচ্ছি
Okay, sorry. So we know importance of cryptography. So if you are using Google and if you click on this log, you will get this kind of message. So this is TLS protocol and we are using elliptic curve every day. We are using also RSA, AES, all this crypto protocol stuff. Okay. And today we'll discuss this part, this RSA part. So RSA is very famous crypto system. It was invented by Rivest, Shamir and Adelman back in 1977 and they published in 1978. And this is the most popular till now public key crypto system, Rivest, Shamir and Adelman. And this is very simple algorithm. And for this algorithm, they got Turing Award in 2002. So now come to RSA algorithm. In RSA algorithm, we have three friends, Alice, Bob, and in middle, Eve. And Alice wants to send some message to Bob, but you know, always somebody is in the middle. Here, Eve is in the middle. So how Alice can use RSA idea, RSA algorithm to send some message secretly to Bob. That I will discuss now. So if you face any difficulty in this algorithm, please raise your hand and ask me. I will again explain. It should be at least this algorithm should be clear for everybody. Okay. So idea here is not only RSA in any public key crypto system that we have two keys. One is public key and another is private key. And this public key should be public. So it should be like I can put in my home page, but I should keep that corresponding decryption key should be that should I keep secret. Okay. So okay. So in Bob's part, Bob will first generate two large primes. It should be it should not be like 3 or 5 or 7, not like that. Then anyone can break RSA crypto system in a 12 bit, or maybe for better security 1024 bit, something like that. So and you know that number of prime is infinite. So we have many primes, and we have some good algorithms to understand that whether some number is prime or not. Miller-Robin test, we call that, or Solvestation test, and we can use that algorithm to generate large primes. Okay, so Bob will do this part. Then he will calculate this product, and we call this n RSA modulus. So n is equal to PQ. Then he will calculate phi n. So numbers which are less than n and prime to n. And it's in this situation will be product of p minus 1 and q minus 1. We can in number theory we know this formula. Okay. Then Bob has to get two numbers E and D. E stands for encryption and D for decryption, so that this guy, this phi n, should be divisor of ED minus 1. And using our extended Euclidean algorithm, you know that simple algorithm, we are learning from that algorithm, from our maybe from primary school to calculate GCD of two numbers. We can use same algorithm with some small tweak to get this E and D. Okay. So this phi n should be a divisor of ED minus 1. And this n should be public. So everyone should know n. And this E, encryption key, also should be private, should be public. But this all other integers like P, Q, phi n, D, everything should be secret. Oh, This is not working properly. Sorry. Okay. To encrypt some message M, instead of sending M directly to Bob, Alice in her part, she will first calculate M to the power E, this integer, M to the power E modulo N, and call that is C, and C is the ciphertext. Okay. So don't send M directly to Bob, send this C to him. So C is ciphertext and C you can, yeah. Now to decrypt this C, Bob knows this D, the decryption exponent. So he will calculate this C to the power D modulo N, and we can prove that this C to the power D modulo N is nothing but M in up to modulo N. Okay, so in Zn, this is basically M. Yeah, that's all. That's RSA. School book RSA crypto system. So any doubt about this algorithm? Because we will, so whole talk is based on this algorithm. We have to understand this algorithm clearly. Any doubt? Okay, very good. So RSA is like padlock, or even any public crypto system is like padlock. You can encrypt, you can lock, but to unlock you need that key. You need decryption key here. Okay. So encryption is very easy because of public key is known, but decryption is really it should be really difficult. Okay. So again, in short, RSA key generation algorithm is like this. You have to generate primes, phi n, and you have to calculate ED equivalent to 1 modulo phi n. And in math, we call this is D is E inverse. If you are familiar with abstract algebra, this is just notation, but idea is same. And encryption is M to the power E modulo N, and decryption is C to the power D modulo N. This is very small example. Of course, in real life, we cannot use this only this kind of 3-digit primes. If you take P equal to this or Q equal to this, N will be like this, and phi N will be like this. If you take public exponent E equal to 13, and you can check this 13 times this, and if you divide by this number, you will get remainder 1. So D in this situation will be this guy. Okay. And to encrypt plain text 1, 2, 3, 4, 5, you have to calculate M to the power N, M to the power E is 13 modulo N, not phi N, because N is public, not phi N is public. And so ciphertext is this thing. Okay. Okay. So suppose another small, you have to do some calculation. Our students. So suppose P is 7 and Q equal to 11, E equal to 43, then what would be the value of D? Can you calculate? So cryptology is not only computer science, this is also branch of mathematics. And in mathematics, you have to do some calculation. I am from math background. Can we find D? Yeah. Great. So I think no, 43, 7, not 7. I am not sure. Maybe my calculation is not correct. 7. Okay. 43. So what should we do? This is democratic country. Either we have to go for voting, or let's so you know calculation. Then so okay. Now this should be. So ciphertext C equal to say 2. Then what will be the plain text? How much? 51? Any? So we are converting 51. Okay. So let's see. Yeah, 51. Great. So now you know school book RSA. Now come to why it works. Now in RSA, we have ED equal to 1 modulo phi n. So you can write ED equal to 1 plus some integer k times phi n. And let us first assume this plain text, this math plain text is in Zn star. That means this less than n, and also co-prime to n. That means GCD between m and n should be 1. So let us just consider this case. Now, so what is C? C is nothing but m to the power e. So C to the power d will be m to the power ed modulo phi n, and ed is 1 plus k times phi n. So you can write like this way. So you are getting m times m to the power phi n to the power k modulo n, and you know m to the power phi n is 1. You know Euler's theorem. So this is 1, 1 to the power k is 1. So you are getting m. So in this situation, your RSA works if m is in Zn star. So similarly, if you take m is in Zn, not only in Zn star, so if GCD between m and n is more than 1, still we can prove that RSA works. Okay. So we need some Chinese remainder theorem, some technique, but proof is not that much difficult, almost straightforward. And you know, if we factor this n, this RSA modulus, because n is public, then we can easily calculate phi n. Phi n is nothing but p minus 1 times q minus 1, and e is public. Then using same Euclidean algorithm, you will get t. And if you know t, then you just crack RSA. You know if you can decrypt it. So this RSA crypto system is based on this problem, math problem, that factorization is hard. If factorization is, if someone can prove no factorization is very easy in classical computer, then next day we cannot use RSA. Okay. But factorization is very classical math problem. It was studied Hermits, or perhaps much before that also, and Gauss also studied this problem, factorization problem. Now we have some algorithm, polar p minus 1 algorithm. If all factors of p minus 1s are very small, then we can use this algorithm. We have another interesting algorithm due to Pomerance, early 80s, quadratic SIP algorithm. Another algorithm is elliptic curve method. If one of that primes, if this n, okay, let me just go. Yeah, if one is suppose p is 500. Normally we are taking p equal 512 and q equal 512. So n is 1024. Now if you take one is say 200 and another is remaining thing 824, then you can use elliptic curve method. Okay, so it should be balanced. Both should be almost same bit size, and that is the hardest situation. In elliptic curve method, if one prime is much smaller, then you can get some advantage. Okay, but now this number field shift, it is the fastest algorithm for factorization when your n is slightly larger, say 100 digits or something like that, 120 digits. So after that, what this number field shift is the best factorization algorithm. And before that, when n is less than 105 digits or 110 digits, before that quadratic sieve is better. Okay, so but since we need large prime, large numbers, large RSA modulus, in practice, we are using this number field shift factorization algorithm. Yeah. And now come to RSA challenge numbers. This is not complete list. From
early 90s, RSA company challenged some, they gave community some really large numbers and challenged the researchers that, okay, factor this number. So you can see, so early 90s, Lenstra factored this RSA 100. So it was 100 digits number. So again, Lenstra et al. Again, 92. And finally, so this is the, I think this is the list. This paper, this RSA 240, which is 240 digits number. It was, I think it was published in Crypto 2020. And after that, that same team also factored this number, RSA 250. So this is 250 digits number. Okay. And this is RSA 250. So this number was like that. And with this team, they factored this RSA 250 equal to this times this. Okay. So for that, they used huge computation, and so it is really, so RSA, you can understand RSA is factorization, large large RSA modulus is still really difficult. Okay. So up to now, any doubt? Now, there is one interesting algorithm due to Peter Shor, 1994. If we have quantum computer, we should have polynomial time factorization algorithm. And so if we have polynomial, we can, if we factor number easily, then we can crack RSA. So that's why if we, this is RSA is not in post-quantum situation, because in quantum, we can factor this publicly very easily. Okay. Now, just one thought, and I got inspired from this website from Henry Cohn. So whether we can do something for even for classical. So just take this function, this L function, e to the power c log n to the power epsilon log n to the power 1 minus epsilon, and suppose epsilon equal to 1, then you can easily prove this function will be n to the power c. So this is exponential, completely exponential. And if this epsilon is 0, you will have log n to the power c. So this is polynomial. Okay. Yeah. So before 1970, this epsilon was 1, so it was exponential. Then in 1981, Pomerance proved that you can take this epsilon equal to half, that quadratic strip algorithm. So after that, Pollard in late 80s, 1988, he invented that famous number field strip algorithm, and so this epsilon is now 1/3. So we are starting from 1, we are up to here 1/3. So now if we can cover this remaining, so we have covered already 2/3 of our journey even in classical. So if we can cover with this 1/3 portion, then even in we don't need quantum. In classical also we can factor. Okay, but after this, more or less this is stable. Of course, many researchers improve this part, this C part, make it more practical, but this epsilon part is still 1/3 from that 1988, 1993, something like that. This is now still 1/3. Okay, so we need some new idea to make it from this 1/3 to 0 for in general. And this is one practical example. This is 512 bit, and this is another 512 bit. This is 1024 bit RSA modulus. And many times we are taking e equal to 2 to the power 16 plus 1, because if you write in binary, you have only 2 ones, and you have advantage in encryption process. Okay. And for this situation, D will be something like this. Yeah. So RSA algorithm more or less over. So if you have any doubt about this algorithm or factorization, we can discuss now. Otherwise, we'll move to. Yeah. Okay, then go to lattice. So still we don't have any in general factorization algorithm in classical computer. In RSA, we have n equal to pq. So if we consider this equation, fxy equal to n minus xy, then how many roots are there for this polynomial over integer? You can take x equal to 1 and y equal to n. Then f1n is 0. Similarly, if you can take x equal to n and y equal to 1, if n1 is again 0. So these two are trivial, and you have two non-trivial roots. One is you can take x equal to p and y equal to q. Then you have n minus p times q, which is basically n. So you are getting 0. So similarly, f q p is again another root. So you have total 4 roots who are trivial. We are not interested of that trivial root, but we have interest if we get that non-trivial roots, pq or qp. And we have another equation, ed is congruent 1 modulo phi n in RSA, second equation. So you can write ed equal to 1 plus some integer k times, and if you expand phi n, you will get n plus 1 minus p minus q. So you can, if you take modulo e, you will have 1 plus k, n is anyhow known, plus 1 minus p minus q. So this is unknown, this is also unknown, and e is known. So if we consider this equation over this ring, then you have root x equal to k and y equal to 1 minus p minus q. Okay. So if we find this root, then, and if this k is less than e, then in some situation you can find this root over, actually not over this modular ring, but actually over integer, and we are done. So our target is to find this root. Okay. So we have two RSA equation. One is n equal to pq, and another is this equation. If we can solve this equation, or if we solve this equation, then we are done. And sometimes we can use lattice to solve this type of equations. Now come to this situation. So let us see. So if you have one polynomials with integer coefficients, so fx is in zx, then there are some algorithms by which we can find the root of this polynomial. Okay. So on the other hand, instead of one variable, if you have more than one variable, say 2 variables or maybe 3 variables in general, still we don't have any efficient algorithm. So for one variable, we have efficient algorithm, but more than one, we don't have any efficient algorithm. Also, if you consider this kind of modular polynomial, where this n should be composite and n should not, you should not factor n. In that situation, if you know factor, then you can solve. But if you don't know factor, then again, this is also, till now we don't have any efficient algorithm. Okay. So this first problem is easy. These or this still we don't have any in general algorithm. Now in this lattice based approach, our target is, we have this kind of equation this equation or this type of equation, and somehow we should do some kind of operation so that we land here. Okay. So that's the overall idea. And so this problem is very close to Hilbert's 10th problem. Hilbert proposed this problem in 1900, and that problem was not actual computation, that is decisional problem. So he proposed that if you have some Diophantine equation, that means polynomials with integer coefficients. Now, can we get some in general algorithm which can tell us that this Diophantine equation has root over integer or not in general? Okay, so that is decisional problem, but here our interest is not only decisional, this is actually computational. We want to get the root exactly. Okay, and I think in 1970, some researchers proved that no, in general, we should not get that kind of algorithm. So even decision is also not possible in general, and we want more. So in general, we cannot solve here, but sometimes using lattice, we can get something in some special situation. So using lattice in some situations, we can change these two problems into this problem, and since we have some efficient idea, we can find the root. Okay, so that's the overall idea. Okay, so come to lattice. So in lattice, we have some, say, omega many vectors, and these are linearly independent. So that means if you consider this matrix, so whose first row is from V1, second row is V2, determinant of this matrix should be non-zero, you know, from your linear algebra code. So these are independent. Now, lattice is integer linear combination of these vectors. So all points are something ai, summation ai, vi. In vector space, we are from field. Here we are from this scalar should be over integer. So if you consider two vectors, v1 equal to 1, 2, and v2 equal to 3, 4, then L will be something like this, and we call this set v1, v2, this set as the basis of that corresponding lattice. Now this basis is not unique. If you start with 1, 0 and 0, 2, again you will get same lattice points. So if you start with 1, 2, and 3, 4, you will have this red dot. And if you start with here like this, 0, 2, and 1, 0, you will get same red dots. Okay. And you can see this is orthogonal, angle is 90 degree, and length is much shorter than compared to this vector. And we call these vectors bad basis, and our target is from this bad basis to move to good basis. So it should be orthogonal and with shorter norm, shorter Euclidean norm. Okay. Now in general, that is very difficult. There are some approximation algorithms, and first algorithm, I think it was due to, this is very, very famous algorithm, triple L algorithm, Lenstra, and Lopez. That's 1982 algorithm. And using this algorithm, we can produce some sort and nearly orthogonal. Okay. So it will guarantee, okay, vectors are within, say, 60 to 100 degree, 120 degrees, something like that. Okay. So if these omega vectors are basis of lattice, then triple L outputs another set R1, R2, R omega with this bound. Norm of Ri should be this, and time complexity is polynomial in this dimension. So dimension here, it should be omega, sorry, not n. So you have omega many vectors. So omega and also bit size of that corresponding matrix. So basically size of that corresponding vectors. Okay. So if you input of triple L is something like this, 1, 2, and 3, 4, you will get 1, 0, and 0, 2. And Minkowski in early, I think 1905 or something like that time, he proved that for lattice there must be one non-zero vector with this bound. Norm of R should be less than square root of omega, determinant L to the power 1 by omega. So here 2 to the power something. So if you put I equal to 1, you will get I equal to 1 means 2 to the power omega minus 1 by 4, something 2 to the power something, but that exponential, but here is square root of omega. So this is existential proof, this R vector, but how to construct this R, that is really difficult. And triple guarantees, okay, we are not giving you this R vector, but instead of square root omega, we are giving 2 to the power something function of omega. Okay. And using this bound, we can do many things. Not only in crypto, in number theory and many other problems also, we can use triple L algorithm. Okay, so how we can find the root? Idea was also due to Hauge-Graham, 1997. So if you have some polynomial over integer with omega monomial, and if root is something over Zn, and if you know upper bound of that root, and if the norm of that polynomial is bounded by this, then this polynomial is actually 0 over integer. Okay, so this is just some theorem. You don't need to remember this theorem. You can just take as a thumb rule. But this again proof is very simple. You can easily check. You need some time to understand, but it is not that much difficult. Okay, so here idea. So it tells us if norm is bounded, then your polynomial is not only over modulo n, but actually over integer, and triple L makes that norm smaller. So this is the connection. So we have some polynomial this. We want to find the root of this polynomial. Just consider corresponding coefficient vector. So this is polynomial. So 1 correspondent. We have some we want to find the root of that polynomial over Zn. So from this fx, target is to find many polynomials with same root, construct lattice. Then triple L guarantees this thing. Again, I'm not considering that initial part. So many times we are neglecting this part because we are working here with really large integers. So many times we neglect this 2 to the power this part. So then if determinant is less than n, then you can find the root. Okay. So I'll give you some examples, then I think it will be more clear to you. Okay. So what is our thumb rule? So forget about triple L, forget about Hauge-Graham theorem. Our thumb rule is determinant L to the power 1 by omega, where omega is the dimension of that lattice. So number of vectors in linearly independent vectors, that should be less than n. So this is the rule. Suppose we have this polynomial fx equal to x square plus ax plus b, and we want to find the root of polynomial. And so from this polynomial, just consider two more polynomials, gx equal to xn. Of course, the x0 is x0n and x0n modulo n is 0. Similarly, if you consider another constant polynomial, hx equal to just n, again h is basically 0 in if you take modulo n. Now construct lattice. So you have three polynomials f, g, and h. From this, and suppose x is the upper bound of this root, then construct lattice from the coefficient vector of these three polynomials. So if you put f x x, so it will be x capital X square, small x square, a capital X small x, and plus b. So you have, this is your first vector. Similarly, this is your second vector. It is coming from g, and this is your third vector. Okay. Now use triple L algorithm. And what is the determinant of this lattice? Just product of this diagonal. This is upper triangular matrix. So x cube n square. And what is our rule? determinant L to the power 1 by omega. Omega here is 3 because you have 3 cross 3 matrix. You have 3 independent row vectors. So its determinant L to the power 1/3 should be, and all are 0 modulo n. So this should be less than n. Now if you calculate, you should get n to the power 1/3. So that means if your root is less than n to the power 1/3, then after lattice reduction, you can find the root. You don't need factorization of n, but still you can capture the root. Okay. So just we should remember only this rule. Okay. Can we improve this bound? So now we have n to the power 1/3. Can we do something better? So up to now is fine. So for the time being, we can forget about that Abraham's theorem proof or actual triple L algorithm. We can use just as a black box, but only we should remember this thing, and so we have to construct lattice in such a way we should improve this bound n to the power 1/3. Okay. So instead of here we are using these 3 polynomials f, g, and h. Now instead of that, if you consider this polynomial f square xf n, nf, n square x, and n square, that means all are now not only modulo n, actually modulo n square. Then if you construct this lattice, so now you have 5 polynomials, 1, 2, 3, 4, 5. So this is 5 cross 5. And if you just do the same rule, you follow this same rule. So determinant L to the power now instead of 1/3, it should be 1/5. Should be now not n. All are modulo over n square. So it should be n square. If you do some calculation, you will get something like this, n to the power 2/5. So from 1/3, we are now 2/5, 0.4. Okay. But we have to reduce this 5-dimension lattice. So in here we have 3-dimension lattice. Now we have 5-dimension lattice. Now instead of 5-dimension, if we go larger dimension, we can improve this n to the power 2/5, n to the power 0.4. And asymptotically, so that means if you give me some idea how to reduce that huge dimension, say 1000 dimension lattice or 2000 in general, whenever everything goes to infinity, we can go up to n to the power half. Okay. So we can find the root of this polynomial x equals x squared plus ax plus b modulo n using lattice reduction whenever the corresponding root is less than n to the power half using lattice idea, using triple L idea. But that is asymptotic. In practice, we cannot go up to infinite dimension, although everything is polynomial, but still it is really difficult to go beyond, say, 500 dimension or something like that. So we cannot do more than that in general, because we are with really large integers. This is not small numbers, so it's really difficult. But up to 400 dimension or 500, even 500 dimension, we can do some lattice reduction. Okay. So this is the idea. So up to now, any doubt? No. So basically, we are not finding the smallest vector. That is really difficult. But we are doing some approximation of that vector. we are trying to find the approximation. So triple L you can see, and let us see. Of course, of course. No, so basically we even for 3-dimension or 5-dimension also we are not finding shortest vector. So here we are neglecting this 2 to the power this part. We are not finding. No, this even okay. So finding shortest vector even for say 100-dimension is also very, very difficult because that is exponential algorithm, 2 to the power 100. But this triple L is not exponential. This is polynomial time algorithm. So here we can go up to say 500-dimension. Okay, but not beyond that. Maybe you can go slightly more. Maybe you can go up to 1000 with huge your computational resource, but not beyond that. And for this, for finding shortest vector, even for I think up to say even for 200-dimension also very, very difficult. No, because it is not basically that is block reduction, right? And it depends upon block. So okay. So yeah, so in we can get better vector, of course, but here anyhow in this analysis we are neglecting this part. Okay. So instead of triple L, even if you have some oracle by which you can find shortest vector, suppose still we cannot get beyond this kind of bound. Taking more time. No, but your thumb rule should be something like this. Okay. So if you get some improved bound, then it is fine. But I don't think. So here you are using some fx times n, something like that, gxn and hx, so everything modulo n square. True. So instead of hx, you want make k times n.
That the lattice volume is more, and then maybe the lattice reduction will be bit easy. I mean, I'm not sure. So have you tried anything?
No, so basically this is very, very only 3x3 matrix, right?
Yes.
So we can get exactly shortest vector also.
Yes.
Okay, so I understand your point. So instead of hx, you are thinking that okay, instead of n, you can take some k times n. I don't know. We have to check whether we get in general better reduction or not.
How good is that if your lattice lattice volume is more, you can do lattice reduction?
Yeah, so we can get maybe some constant improvement. Instead of n, you can put some
Yes.
small. Yeah.
And the volume will.
Yeah. So maybe we can get something, but main idea is whether we will not multiply that same k here, right?
Yes.
Or we will multiply there here also.
Yes.
Again here also.
Yes.
Okay. So okay, we have to check.
So your lattice vector will be k times.
Yeah, k basically k cube times
Yes.
original.
That you will get, but that might be short enough to I mean, I'm not sure, but this
Okay, then we have to, because in my opinion, triple L is still mystery. So this is just black box, it is giving something. But actual performance is much, much better than that 2 to the power that approximation thing. We have to do some experiment. Okay, so in practice, I don't know, but if you go this theory, you will not get any improvement. You will still get n to the power 1/3. Similarly, instead of 3 dimension, you can go 5 dimension, and we get some n to the power 2/5. Again, this is only 5 cross 5 reduction is very fast. Even you don't need triple L algorithm. You can use some shortest vector algorithms, and asymptotically. But asymptotically, you have to go some huge dimension, say 200 dimension. There you cannot find shortest vector. Then so you have to do some reduction using triple L type idea. Okay, and finally we will have this bound n to the power half. Yeah. So any other question? Okay. Then let us move this. So suppose prime P is something like this. Of course, this is not RSA prime. This is very small, only few bits. And suppose you know this portion. This we call this portion MSBs, most significant bits. Somehow you know this portion. So you know P0. So this block is same as this block, and remaining P0 can make all 0. So you know some approximation of prime, which is called P0, and this is unknown part. This is X0. So what is X0? X0 is nothing but P minus P0. Now, if you consider this polynomial fx, which is P0 plus X, then you can check if X0 is 0 modulo P. Okay. And we don't know P, but we know multiple of P, that is N, and we know P0. From this information, can we find this X0, this unknown part, using lattice idea? Now, suppose this unknown part is bounded by capital X. So here our target is to find this X0 from this polynomial fx and from this RSA modulus N. Now, how we can do? So just like last idea, so consider this 4 cross 4 matrix, n square, nf. Nf is basically n f x0 is 0 modulo n square, because fx0 is 0. Fx0 is 0 modulo p. Sorry, so okay, sorry. It should be modulo, all are modulo p square. This is p square, this is also modulo p square, this is modulo p square, p square. So our rule is determinant L to the power 1/4 should be less than p square. Now, if you calculate, and since I already told you that in RSA both primes should be more or less same size, so you can approximate this p by this by n to the power half. Of course, there must be some constant, some 2 or 3, not more than that. So if you plug all these things, you will get x should be less than n to the power 1/6. Okay. So if p is like this, and if you know this portion, we can find the remaining portion whenever that remaining portion is less than n to the power 1/6 using this lattice. Now, in general, we can define like this polynomials. So pix equal to like this, and p dash ix equal to like this. And if you do some calculation, it is not difficult, but you have to do some calculation. Finally, you can prove that if mod of p minus p0 is less than n to the power 1/4, then you can find the root. Okay. So that means if you are using 512 bit primes, and if somehow somebody gets, so say 256 most significant bits of that prime, then remaining 256 one can find in polynomial time using lattice reduction. So these are some. So Rivest and Shamir in Eurocrypt 1983, they proved that if you know these 2/3 LSBs, this portion, then you can factor n. Coppersmith proved that if you know instead of 2/3, if you know this portion only half, 50%, it was 66%, now 50%. If you know this portion, then you can find the remaining portion in polynomial time using reduction, using almost same idea. Pone et al. In Eurocrypt 1998, they proved that if you know this portion, this LSB portion, least significant portion, then also you can factor. And Hardman and May in Eurocrypt 2008, they instead of they just considering only one block, one known block, they consider few known blocks. So suppose this is known like that. And they studied this problem, and they proved that asymptotically, if you know 70% of the prime, then you can find the remaining blocks, but time complexity will be exponential in number of unknown blocks. Okay. So suppose this portion, this would be 70%. Yeah, some that is something, some fault data. No, so there is so that means this is just we don't know this is optimal, right? Maybe somebody can get some better polynomials. Yeah, of course. Yeah. So only if you have this polynomial, then you have this bound. Similarly, we have second RSA equation, ED equal to 1 modulo phi n. So we have this equation we have already discussed. So we have this equation. Now, if you consider this polynomial over this polynomial ring, and we want to find the root of this polynomial, Pone and Darcy in Eurocrypt 1999, they prove that if d decryption exponent is less than this bound n to the power 0.292, then one can find the root of this polynomial. So if you know the root of this polynomial, you know k, 1 minus p minus q. So you know p plus q, you know product. So you can find p and q. Okay. So if your n is 1000 bit, and if your decryption exponent is less than 292 bits, then in polynomial time one can factor n. Although 1000 bit n, if you give only 1000 bit number, perhaps it is really difficult. But if you give 1000 bits together with public key, that should be enough for polynomial factorization. Okay. And this is some result from late 90s, 1999, and they conjectured that using this lattice idea, one can go up to n to the power 0.5. So it is n to the power 0.292. They first proved n to the power 0.284. Then after that, making everything very, very complicated and using some sophisticated calculation, they improve little bit n to the power 0.292 from n to the power 0.284. Then finally they conjectured this lattice idea should work up to n to the power 0.5, and this is still open problem. So even if you go up to n to the power 0.1/3, that's also very, very good result. So what is their idea? So this is our polynomial. From this polynomial, this is our f. So from this polynomial, just construct this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Some 12 polynomials. Yeah. Okay. So this p and q both are around n to the power half. So p plus q is around n to the power half. Yeah, balance prime. Yeah. So here we are considering only balance prime because balance is more difficult situation. Okay. So if this is not balanced, if p is much smaller than q, then you can improve this bound. But idea is exactly same. Only you have to do some little bit calculation here and there. Nothing new. So if you consider this polynomial, and if the bound of k is capital X and bound of y, this value is y, and normally we take y equal to around n to the power half and construct lattice, then finally your lattice will be something like this. The determinant will be something like this. And what is our thumb rule? Determinant L to the power how many vectors? Perhaps 12 vectors. So determinant L to the power 1/12, and everything are modulo e cube. So this is 0 modulo e cube. This is also 0 modulo e cube. So all are basically 0 modulo e cube. So this to the power 1/12 should be less than e cube. So finally, this is the bound. And after lattice reduction, if we get to these two polynomials whose roots are x0, y0 over now not only modulo n, modulo e cube, but over integer, then using some idea like Ropner basis or resultant, you can find the root. Again, this is, yeah. Yeah, because determinant calculation is easy. Yeah. Other, because we have to analyze asymptotically. Yeah. Yeah, so this is one is triangular matrix and another is, you can see matrix is square matrix, but lattice definition is not square. Okay, so then you have some rectangular matrix, and there is also concept of determinant, but that is calculation is much difficult. Okay, basically this bound, this n to the power 0.292 bound, this is not from square matrix, this is rectangular matrix. And for square matrix, bound was n to the power 0.284. So only small improvement, but now from square you have rectangular matrix, so determinant is really difficult, and yeah. Yeah, any other doubt? So after reduction, if we get these two polynomials, then we can use some algebraic technique to find the root. Again, this is under some assumption. So this result, this bound n to the power 0.292 bound, These are heuristic. It works in practice, but this is not, we cannot write theorem and proof, because here we are assuming some algebraic independence. If you assume that thing, then this is theorem and proof. Okay. So in general, they used this type of polynomials, and using this type of polynomials, you can get this bound. Okay. This bound, not exactly this bound, n to the power 0.284. Okay. Now come to another type of attack, which is known as partial key exposure attack. And in this partial key exposure, we are assuming that we know some bits of, say, primes or decryption exponent. So target is whether we can recover the remaining portion using this type of attack, practical attack. I don't know. I am not from hardware background, so I don't know. But there are some idea by which you can find the some bits of decryption exponents or primes, like that. Okay. So in partial key exposure, this is your secret key, and we call this portion most significant bits, this portion least significant bits. Here we are assuming that we know this portion or this portion, and target is to find the remaining portion. So what is target? So suppose we know this key most significant bits, and we have to minimize this key so that from this knowledge we can recover the remaining portion. Okay. Now using lattice idea, we can do. So what is our RSA equation? RSA equation is it equal to 1 plus this k times phi n, and we know MSB portion. So you can write this d equal to d0 plus d1, where d0 is known portion and d1 is unknown portion. So you can write like this way. So we want to find the root of this polynomial over integer. And this polynomial was studied by Ernest, Josemes, May, and Wagner in Indocrypt 2005. And there are many attacks in this line. So I already told you this paper. Also, Blomer and May, Crypto 2003, ANO, PKC 2009. We also did something in Indocrypt 2010 and 2011. Also, people Takayasu and Kunihiro in SAC and CTRSA. Okay, so people studied partial key exposure attacks on RSA, and it is getting improved and improved. This is we improved this work here, but not in theory, in practice. So here, if it takes a 1 hour, then here it takes 20 minutes, like that. But this is only actual practical experiment, but theoretically this bound is still better. Okay. So now this paper little bit improved in LSB situation, and here I considered that instead of only one block, if we know many blocks, like that, this Indocrypt paper. Now another very important RSA variant is one important variant is CRT RSA, Chinese remainder theorem variant of RSA. And many times we are talking, okay, RSA is working, but not RSA. Many times this is actually Chinese remainder theorem variant of RSA, and it is around 3 to 4 times faster than RSA. It is used in OpenSSL, Java, .NET, and here instead of in RSA we have only one decryption exponent. Here we have two decryption exponents, dp and dq, with this equation. So edp equal to 1 modulo p minus 1 and edq equal to 1 modulo q minus 1. Okay, so you have now two equations. And like RSA, people also tried to analyze when dp and dq are really small. Josemes and May in Crypto 2007, they proved whenever this dp and dq are less than n to the power 0.073, then you can factor n in polynomial time. So whenever your n is 1000 bit, and if both DP and DQ are less than 73 bits, then you can factor. Now, after that, after 10 years, Takayasu, Lu, and Peng, they improved this bound n to the power 0.073 bound to n to the power 0.091. And this is very, very important result. Just after Eurocrypt, they improved their own result, and finally they published in Journal of Cryptology with this bound n to the power 0.122, and this is the best result in this CRT RSA for small decryption exponent. Okay, so let us see the idea in CRT RSA. Of course, we have n equal to PQ. We have already that equation, and we, instead of one equation, now we have two decryption exponents. So two decryption equations. So EDP equal to 1 modulo, it should be P minus 1. So EDP equal to 1 modulo P minus 1. So you can write EDP equal to 1 plus K times P minus 1. So similarly, EDQ equal to 1 modulo Q minus 1. So you have EDQ equal to 1 plus L times Q minus 1. And we have this third equation. So in RSA, we have two equations. Here we have three equations. Now, Joseph and May considered this expression. EDP minus 1 plus K times EDQ minus 1 plus L. So what should be this value from these two equations? Can you guess? Sorry? KLN, right? So basically EDP minus 1 plus K equal to K times P. Similarly, this is also L times Q. So KL and PQ is N. So this is basically KLN. Now, and using this equation, they got this bound, this n to the power 0.073 bound. Now, Takayasu, Lu, and Peng, they considered these three equations. So one is 1 plus K times P minus 1 is 0 modulo E. Now, if you multiply with P here, so you have E dq P equal to P plus L times PQ is N. So N minus P is again, this is 0 modulo E. And also, if you take modulo E over here, so this will be 0. So this EDP will be 0, 0 modulo E. So you have K minus 1 times L minus 1 minus KLN equal to 0 modulo E. So here, in that Crypto 2007 paper, they considered one equation. Here, they used these three initial equations, and also they developed another some three auxiliary equation, and this method is really complicated. And finally, they obtained this bound. Sorry. They have first obtained this bound. Again, with some small tweak, they get this improvement. Okay. So technique of 1 is completely different. Technique of 2 is completely different from 1, but 2 and 3 are more or less similar technique. Only some tune of parameters. And we also did something on partial key exposure. First in SCNS, then Indocrypt, again Takayasu and Kuni or Hiro. They also considered this partial key exposure in SCNS and ISC. And recently, last Asia Crypt and this year Eurocrypt, we considered partial key exposure on CRT RSA when decryption exponent D is encryption exponent is full size. Okay, but okay, I'll come. Okay, these are some open problems. So one very interesting problem is this: whether we can improve this Bonet-Darcy alt result, Bonet-Darcy bound, or we have to prove that no, if we cannot improve. At least that is idea. We should not go beyond n to the power 0.292. This is very important result, and I think many of us who are working on this RSA problem tried this to improve this bound. I have no idea. Many are young researcher or senior experienced researcher. Maybe we can discuss and maybe we can get some new idea to improve this bound. Okay. And another interesting is to improve this TLP bound. Now it is n to the power 0.122. This GOC result. Okay. This result. Now can we go beyond this? This is also very important because CRT RSA is very practical. So anything beyond this bound 0.122 is it should be really interesting. And also another interesting problem is in our this Asiacrypt and Eurocrypt paper, basically Asiacrypt paper, we consider E is of full size and we assume that we know decryption exponent of DP and DQ from LSB portion, not from MSB portion. Okay. Now, can we get similar kind of result if we know from the MSB portion of DP and DQ? That is also. So, partial key exposure attack on CRT RSA whenever E is full size, and if we know MSBs of that decryption exponents DP and DQ. So of course there are only some 3 problems, but there are many interesting problems on RSA and its variants, CRT RSA, count prime RSA, prime power RSA, many variants are there. So these are all interesting problems. So for reference, you can read this paper, Journal of Cryptology paper, and also this is very easy to read, I should say. Basically, I read this thesis during my PhD time, this 2007 thesis. You can, if you like, you can try to read this thesis, PhD thesis, and also this is really nice survey article. So these are you can try this. This is Coppersmith paper is little bit difficult, but this is original paper, so I should put in this list. But this is also, and this 2 and 3 are really important, interesting, easy to read, I should say. And I'm from High Madras. All are welcome to come here. We have beautiful campus. You can see many beards. Okay. So please come and we have now many cryptographers. I am from that department. We have cryptographers in computer science department. So I hope that we can have some joint collaboration. Okay. And if all my informations are given here. Yeah, thanks. Yeah. I have no idea. I I tried this problem, and I know many researchers also tried this problem. This is a really classical problem. This is relatively new problem because now this is more than 20 years. This is only 5 years. So perhaps this is more practical. And this paper is really difficult. And but if you understand, this is a really interesting idea. So maybe we can get some idea from this paper and into this bound. And in my opinion, perhaps this should be simplest because this is only last year SHS paper, only 1 year is over. So maybe this is slightly easier than. So this is in that hardest, let's that, and perhaps this should be, we should try first 3, 2, and then 1. Thank you very much. And if you have any doubt, you can mail me.
So we are in the end of the morning session. We will have a lunch. Now lunch break is there. There is a small announcement that the persons who have Indian mobile numbers, can access Wi-Fi Bose Institute. And if we foreigner don't have any Indian mobile number, please meet me. I will share the Wi-Fi password for them. Thank you. We can meet in the lunch hall. And the next session will start at 2 p.m. Thank you.
Done.